Control of risk for hydrogen embrittlement in steels for automotive applications. It's an RFCS project, a research fund for coal and steel. It started in 2020 and finishes now, in fact, tomorrow, at the end of June in 2023. The consortium is composed of 6 different partners. 3 of them are industrial partners, 2 steel makers, voestalpine and ArcelorMittal, and 1 car part manufacturer, CRF, and 3 research entities, CRM and Letomec, that is a spin-off of the Pisa University, and Eurecat. And in this project, Eurecat is the coordinator. So an interesting news was published at the beginning of this month in a business and financial magazine called Market Watch. And this article says that the advanced high-strength steels in automotive market is projected to experience growth in the forecast period of 2023 to 2030, as shown by new trends analysis and competition tracking with a complex annual growth rate of 30.6%. And why is it important to use advanced high-strength steels? Because we all know they have exceptional properties such as high strength, they show excellent formability, low weight, greater deformation before reaching the elastic limit, and all these properties makes them perfect for manufacturing structural and safety components of vehicles, improving in terms of safety, car efficiency, and reducing the emissions. But they are not all advantages. They show some challenges for manufacturing them. For example, tool wear or a spring back. They show crack sensitivity, especially at the edges, and show hydrogen embrittlement susceptibility. So the Crystal project is focused on the study of hydrogen embrittlement of advanced high-strength steels for automotive applications. Here, there are the main objectives of this Crystal project. We have 6 different objectives. First, validate the hydrogen embrittlement risk in advanced high-strength steels parts for automotive industry. Study the effect of hydrogen content on advanced high-strength steels in 2 types of these steels, in cold-rolled steels and in press hardening steels. Determine the hydrogen threshold content that drastically reduces the mechanical properties. Use a novel non-destructive methodology, in this case a solid-state gas sensor, to quantitatively measure in situ the hydrogen absorbed during real production steel parts. The 5th objective is to perform a range of laboratory tests and also a real plant tests to optimize or to find which is the best method to determine the hydrogen embrittlement susceptibility of this type of steels. And finally, the last objective is to increase the knowledge or the understanding of the hydrogen embrittlement uptake mechanisms to elaborate future norms and production and testing. Atomic hydrogen absorption in automotive components can take place at different stages of the car part manufacturing and also in service life. For example, in car part manufacturing, the most critical points is during steel production, during forming, it means cutting, joining, forming also, and then in pre-treatment, that includes e-coating, etching, and all these steps. The hydrogen that can be absorbed during the car part manufacturing is called internal hydrogen. And then the hydrogen that is generated during the reactions of oxidation and corrosion reactions during service life and can be absorbed in the microstructure, it's called external hydrogen. So we think that it's very important to know the effect of the internal hydrogen and the external hydrogen on the mechanical properties of these advanced high-strength steels. So the Crystal project focuses on these 2 types of hydrogen steels, of hydrogen, internal and external hydrogen. Sorry. Here is the general project overview of the Crystal project. Later on, we will discuss in more detail each of the work packages. The work package leader is detailed in each yellow star. So we have 7 work packages. The first one is the coordination. Then we have a work package 2, where we selected the advanced high-strength steels that we wanted to study in the Crystal project. The leader is ArcelorMittal. In work package 3, we optimized the charging methodology to charge these cold roll steels and press hardened steels. The leader was CRM. In work package 4, we performed all the laboratory tests to study the internal and external hydrogen effect. Eurecat was the leader. In work package 5, we studied the effect of hydrogen in real industrial plant. Letomec was the leader, and in work package 6, the leader was CRF, studying the life testing, performing different corrosion tests. And finally, all the results are summarized in work package 7, where we have to define which is the best methodology and the best test to identify the susceptibility or to quantify the susceptibility of hydrogen embrittlement of these advanced high-strength steels. So if we move in more detail to all the work packages, and we start with work package 2, we selected 4 steels, 2 cold-rolled steels, in this case CP1200 electrogalvanized from voestalpine, MS1500 also electrogalvanized from ArcelorMittal, and the press-hardened steels were PH1500 galvanized from voestalpine, UC-Bor 2000 with aluminum silicon coating from ArcelorMittal. And we performed the same, or the general characterization. In terms of mechanical properties, also we evaluate or analyze the microstructure, and we determine the hydrogen content and this steel process. We used 2 different techniques, LECO DH603 from voestalpine and a TDA equipment from ArcelorMittal. As you can see, the hydrogen content measured was from 0.07 to 0.11. So the hydrogen pickup during the steelmaking process is very low. Doing this hydrogen content characterization, we realized that inside the consortium we have 5 different laboratories with facilities to measure the hydrogen content. So we thought that it was very important to define if the hydrogen content measured in all the labs were more or less similar, or which was the scatter that we have in this value. So in the table on the right, you can see all the techniques or the methodology that we have in our consortium. So we can see that we have hot extraction, we have micro GC, hot extraction with different gases. Also, we have different heating rates, different maximum temperature, and different holding time. So CRM was responsible for charging, in this case, a PHS 1500 with 0.5 ppm of hydrogen, and then we sent to all the partners. And we measured which was the content of the hydrogen. And as you can see in the graph, we considered that all the hydrogen measurement in the consortium were acceptable. So here is the work package 3, where we optimize the charging methodology for these 2 types of steels. So in the case of cold roll steels, we electrocharge using a mixture of sodium chloride and ammonium thiocyanate. And we have to remove the zinc coat again, then hydrogen charge, and then to apply a zinc coat again to keep the hydrogen in the steel, in the microstructure. So we have to optimize these 3 methodologies: how to remove the zinc, how to charge the samples or the cold roll steels, and then to zinc coat again to obtain a tiny and a dense zinc coating. And in the case of the PHS steels, we hot charge this type of steels, modifying the dew point, the atmosphere, the holding time, and the temperature. Later on, Mélodie Mandy will explain how the optimization of these charging methodologies. Our hydrogen content target was between 0.51 ppm. We know that this value is far from the reality, but we had to fix at least 2 hydrogen content to perform the test in work package 4. Okay. In this work package, also we characterize in terms of diffusivity, electrochemical permeation, and solubility. Here is the work package 4, where we perform all the laboratory tests. As I said before, we divided this work package into big tasks to measure the internal hydrogen effect and the external hydrogen effect. And we had several meetings at the beginning of the project to decide which was the best sample geometry to perform all the tests. And in this case, we selected a plain sample to perform the U-bend and the 4-point bending test, and a CEP 1970 for all the tests, except the cracking resistance. And also we had several meetings to define how the samples had to be prepared. In the case of the PHS steels, the PHS manufacturers send the blanks after charging, so they send to CRM the blanks, CRM charged the samples and then sent to the partners. Each partner was responsible for laser cut the edges and laser cut the holes in this case. We have to include also that for the PHS steel 1500, we had to remove the zinc, charge the samples, and apply the zinc again. And in the case of cold rolled steels, the steel manufacturers sent the blank to all the partners, and each partner was responsible for charging the samples. So as I said before, removing the zinc firstly, then electrocharging, applying the zinc coating again, and then we agreed to shear cut the edges and punch the hole. In the case of external hydrogen, the samples were the same and the sample preparations were also the same, but we added a last step that it's paint baking treatment to be closer to the reality. Also, we have to say that in the case of the PHS steel, we realized that it was very difficult to introduce hydrogen to the materials, so we decided to study how was the effect of hydrogen if we have different coating treatments, in the case of UCBOR and PHS steel. So here are all the tests that we perform in this work package. So in the case of studying the internal hydrogen, we perform 4-point bending test, U-bend, constant load test, slow strain rate test, list, and cracking resistance in the as-received condition and after pre-charging. In the case of external hydrogen, we perform 4-point bending test, U-bend, constant load test, a slow strain rate test, step load test, also in as-received condition, after pre-charging, and in aggressive media. We decided to test these samples in immersion and in salt spray test. Anis Aouafi, later on, will explain the most important results of this work package, of this test. And on the right side, you can see some images of the test. So on the top right, you have the cracking resistant tool that Laura mentioned sometimes today. On the top left, we have a 4-point bending device. On the bottom right, a 4-point bending test in immersion. And on the top left, a slow strain rate test. Also, I would like to add that in all the cases, we measured the hydrogen content before the test and after the test. Because in some cases, for example, in the constant load test, the duration of the test is quite long. So we wanted to be sure that we don't have hydrogen uptake during the test. I mean, the gaseous of the hydrogen during the test. So in work package 5, we study the effect of hydrogen, but in real industrial processing. We evaluate the core formability, performing the Hall expansion test at different hydrogen content. Also, we evaluate the effect of painting in different conditions, and we perform a 4-point bending test of different type of painted samples. In basic E-coated samples, an E-coated plus stone chipping samples, and an E-coated plus scratch samples with 2 different stresses. Okay, these samples, we evaluate the hydrogen susceptibility, introducing them in immersion and also in salt spray test. And finally, Letomec measured the hydrogen content in different stamping conditions. At the end of this session, Linda Bacchi will show you some results of this hydrogen measurement in modifying the stamping conditions. And in work package 6, we performed the live testing. Here it was planned to do the 4 live tests, but due to economical reasons, CRF couldn't perform it. And we decided to increase the number of the samples tested in cyclic corrosion and increasing the number of inspections. So the selected cyclic corrosion tests were SAE-JAI 2334, and we tested the same samples as in the painting in work package 5. So the samples E-coated plus stone chipping, and E-coated with scratch with different 2 stresses. And in work package 7, we are analyzing all these results, and we are writing, these days, we are writing a guideline for the car part manufacturer and also for the steel manufacturer to select which is the best methodology to charge the samples and the best methodology to test the hydrogen embrittlement of these types of advanced high-strength steels. So this is a general view of the project Crystal. And now I would like to introduce Mélodie Mandy. I don't know if she's connected. Mélodie? Hello, Mélodie.
Yes. Hello, I'm here, yes.
Hello, Mélodie. So, Mélodie works in CRM. She is a senior project leader. She is working in the field of hydrogen-metal interactions and more specifically on the mechanism of hydrogen uptake and release in coated steels. So, Mélodie, the word is yours.
Thank you, Sílvia. Thank you for the introduction. So I will share my screen directly so that you will see the presentation, I hope. I hope you hear me well also. So thank you for the introduction. So as Sílvia told, I come from CRM Group. So firstly, just 2 words about CRM. So CRM stands for Center of Research in Metallurgy. So we are a research center which is located in Belgium, which was founded 75 years ago. And we are among 270 researchers that are dealing with different aspects of metallurgy. Our global approach is really dedicated to a global approach which considers the product, the process, and the application. And we generally work from the lab scale until the different pilot lines that we have for industrialization. We work for a certain number of members that are usual clients and for also other private clients. Our activities are focused around 6 different axes. The first one is really our core business and is dedicated to this process, product, and application development. We also work on the energy shift, on the advanced manufacturing, the industry 4.0 and digitalization, as well as the circular economy and the construction. So this presentation, as Sílvia introduced it, will be focused on the third work package of the Crystal project. So the main objective of this work package was to optimize the charging condition of hydrogen in the 4 different materials that we have tested in the Crystal project. So in this work package, the partners that were involved were the Letomec and ArcelorMittal and the CRM Group. So for Letomec and ArcelorMittal, you will see also Linda and Anis just after this presentation. And so globally, the objective of this work package, it was firstly to optimize the hydrogen charging protocol. As Sílvia told it, it was different for cold rolled steel than for press hardened steels. To study also the effect of the different parameters of this hydrogen charging on the diffusible hydrogen content. And afterwards, the other objective was also to characterize a bit the global system in terms of hydrogen behavior in those different metals. So we speak here about hydrogen traps on one side and on hydrogen solubility and permeability on the other side. So I will come back on those different aspects. So let's begin with the hydrogen charging of the cold rolled steels. So here we come back to the slide, to the general strategy that Sílvia has shown you very briefly during her presentation, sorry. In this case, for the cold rolled steel, we have performed electrochemical charging. So this was decided just in terms to be representative of what is done or what can appear in the industrial reality. So in the case of cold rolled steels, when we received them, we were first forced to remove the zinc coating as those materials were electrogalvanized, and then perform the electrochemical charging. So this was performed mainly at ArcelorMittal for 2 different grades, so the MS 1500 and the CP 1200. So for the zinc removal, it was a quite basic method with pickling in HCl and HMTA solution. And after that, the electrochemical charging was performed. So basically, electrochemical charging consists in putting your sample that you want to charge in hydrogen as a cathode in an electrochemical cell, and you will generate hydrogen at its surface. Part of it will recombine into H2 and H2 molecules and degas, and part of the hydrogen will enter in the material. In this case, we have worked with water and a sodium chloride solution in which we have added various amounts of ammonium thiocyanate, which is actually a recombination poison. So this means that this molecule will inhibit the recombination of hydrogen atoms into H2 molecules, and so limit the degassing into gas molecules and favor the entrance of hydrogen in the material. So we applied a given current density, and we made vary the duration of the charging. So here you can see a brief insight of the results. So you have on the left side the results in terms of MS 1500. I will take the pointer, it will be more easy. So you have the results for the MS 1500 on the left, for the CP 1200 on the right side. So what you see is the desorption rate as a function of the desorption temperature for the different conditions. And you see in the table a rapid summary of the hydrogen amounts obtained in the different conditions. So with various amounts of ammonium thiocyanates and various charging times. Globally, what we can remember is the fact that the longer the charging time, the larger the diffusible hydrogen content. We see also that when we increase the recombination poison concentration, we obtain larger diffusible content, which is logical, as we force hydrogen to enter in the material. When we compare both steels, also you have the graph on the right side here, where you can see that in equivalent conditions, we see that the hydrogen uptake will always be a bit larger for the CP1200 than for the MS1500. And finally, ArcelorMittal verified also the reproducibility of those electrochemical charging by reproducing the different treatment in different baths several times. So that was for the part about the electrochemical charging. Then, as Sílvia told, we had also to zinc coat again those material in order to impede hydrogen degassing. So we want to charge them, but we do not want them to degas too rapidly, because we wanted after that to make some mechanical testing, and also we need to transport the samples. For this zinc coating, a specific methodology was also developed at ArcelorMittal with a specific solution. So it consisted in electrodeposition of zinc to obtain this hydrogen tight coating. So the conditions are here. So I will not enter into the details, but the result is the fact that zinc coating developed by ArcelorMittal was proved to be tight to hydrogen diffusion for at least 1 week, which is a sufficient duration for our mechanical test and for the transportations. So now for the press hardened steel, so we are on the other topic. For that part, the strategy that was followed was to charge them with what we call the hot charging. So it's actually a gaseous charging in a furnace. So this was performed for both press hardened steel, so UZ-bore 2000 and PHS 1500. It has to be mentioned that UZ-bore 2000 is a material that was coated with an aluminum and silicon coating, while PHS 1500 was actually with a zinc coating. It was actually a GA, so a galvanized coating. In some words, so for the gaseous charging, we performed with steel sheets, with already steel sheets, so 160 millimeters by 200 millimeters. The gaseous charging consisted actually in an austenitization heat treatment that was performed in a controlled atmosphere furnace. According to specific conditions that we chose in order to fit with process windows of both steel. So you see finally the conditions that were chosen here in the table. On the right side, so globally the austenitization temperature was 900 degrees or just below or just above. We have defined several holding times as soon as we reached a temperature of 870 degrees Celsius, and we tested also two other parameters of the atmosphere. So firstly, the dew point. So the dew point was varied from -20 to +15 degrees Celsius. So the dew point is actually an image of the humidity that you can find in the atmosphere of the furnace. So that's why you have the conversion into percentage of water just next to the dew point. So the higher the dew point, the wetter the atmosphere in the furnace. And another point that we made vary is the carrier gas. So in most conditions, we worked with air, but we worked also with nitrogen. So you will see why just after. On the principle, so you inject your carrier gas, so either air or nitrogen. One part goes dry in the furnace, and a mixture is made with a certain amount of the gas, which is humidified in a liquid tank of liquid water. Sorry. It goes in the furnace, and then we have some analyzers just to be sure about the atmosphere that we have in the furnace. What is interesting to mention also is the fact that we are able to work with deuterium, and I will come back on that aspect at a later stage of this presentation. And after gaseous charging, so we perform the thermal desorption analysis. So thermal desorption analysis, in what does it consist? We put the sample in a furnace. We heat the sample at a given rate. So here it was 20 degrees Celsius per minute until a temperature of 400 degrees. And by doing this, we let hydrogen that was absorbed in the material desorb, and it will be carried away by a nitrogen, which is inert here, carrier gas, until mass spectrometer to be quantified. So here you see just a small picture of the equipment. So here is for the results for Usibor 2000. So here we have decomposed both of them. So firstly, on the top left, you see the effect of the holding time. So we made vary the time between 1 and 5 minutes. You see that the effect is quite limited in terms of hydrogen uptake. So you see here the diffusible, what is called HDIF, is the diffusible hydrogen content, which is always in the y-axis, as a function of the parameters that we deal with. So in terms of holding time, we have quite limited effect, and it's also the case with the temperature. So the temperature was really slightly varied. We are really in the process window of the steels, so we have only adapted the temperature by 20 degrees Celsius, and you see that in that studied range, we have very few impact. On the right side, we will see a more important impact. So it's more about the atmosphere parameters. So you see first the dew point, so which is represented here. So you see that the higest the dew point, so the wetter the atmosphere, the higher also the diffusible hydrogen that is absorbed during the austenitization process. Below, you see the effect of the atmosphere. So here we made two tests between air and nitrogen, and we see that there is really a strong impact. When we work with nitrogen atmosphere, we have diffusible hydrogen contents which can be really larger. So this is typically something that is not at all used industrially, but it was interesting in the framework of this project in order to enhance hydrogen uptake and to reach, I would say, extreme conditions in this case. So that was for Usibor 2000. So the same work was performed for PHS 1500. It was a bit different in this case because we had encountered many difficulties to charge these materials with this zinc coating. So in the end, for the sake of this project, we were forced to charge this material by removing firstly its coating. So the result that you see here, it's not about PHS 1500 GA, but bare PHS 1500. What you see is that what we have seen just before for the conclusion that we have seen for Usibor 2000 are quite the same for these bare materials. So you see that we have a strong impact of the atmosphere. So in nitrogen atmosphere, we have a larger uptake than in air. We have also this effect of the dew point, which is well marked. And the effect of the holding time and the temperature are maybe a bit less marked, a bit less significant than for PHS 1500, but remains less important than the atmosphere effect. So that was for the hydrogen charging. So now in terms of characterization of the system, at Letomec, they were able to characterize the diffusivity and the solubility of the four materials that we work with in the crystal project, owing to a specific tool that they developed. So it's called the Helios 2 probe. It's based on the principle of an electrochemical permeation cell, but with a solid state sensor. So the different conditions that were used are given here. I will not enter into the details, but the principle is the one that is highlighted here. You put hydrogen on one side of the material, you detect which amount and in which time it will arrive to the other side, and you have a graph like this one with the hydrogen flux as a function of the time. The diffusion coefficient, which is here the D in the equation, is defined based on a method that they have chosen, which is found in the literature, as a function of the time required to reach a certain level of the regime flux of hydrogen diffusion through the steel. Some words about the results. So typically results that you can obtain here, for instance, for the MS-15. So they perform these tests on the bare steel and also on the zinc-coated material, or the aluzi-coated material for the Usibor 2000. In each case, the coating was only on one side of the material, just to see its effect. And you see a bit the typical experimental curve that you can obtain. In terms of results, what we see is mainly the diffusion coefficient, of hydrogen that is summarized here in the table. You see that mainly what we could expect also is the fact that the presence of the coating generally hinders hydrogen diffusion, so diffusion coefficients are smaller. Diffusivity in bare colored steel is quite similar in both of them. And for the PHS steels, we see that Usibor 2000 apparently shows a slightly slower hydrogen diffusivity than PHS 1500. So this leads me to the final part of this presentation. A last thing that we had to do in this part was to characterize those materials in terms of hydrogen traps. So what was performed here is globally the same methodology as just before. So firstly, we charged the samples with hydrogen. So again, it was performed using electrochemical charging for cold-rolled steels and using gaseous charging for PHS. Specificity here is the fact that we used deuterium for this study at ArcelorMittal and at CRM. So deuterium is the hydrogen isotope with one more neutron. It is very interesting because it's far more scarce than hydrogen. So we are sure that we can perfectly identify it when we found it in the results. This was also performed on bare steels in both cases, not only for PHS 1500, because in the case of the presence of a coating, this will induce a step of diffusion that will be slower and that will have an impact on the results. So after that, we performed the thermal distortion analysis with various heating rates, and we applied the Kissinger methodology. So basically, the idea is that when you have a graph like this for one given material with different heating rates, you have a peak temperature which is different at each heating rate. You use this temperature that you put in this equation, and you will find the activation energy that we found here for the material. So as you can see, we have activation energies for detrapping of hydrogen, which are quite close. And here we are convinced that it is corresponding to reversible traps that are likely dislocations for those materials. So this is the end of the presentation. So for the conclusion, we have charged hydrogen in the 4 different materials with more or less difficulties depending on the material. We see that we have some impact of specific parameters like the time and the Poisson concentration for the cold-rolled steels, like the atmosphere for the press-hardened steels. We were also able to test diffusivity and permeability of hydrogen through those materials with and without the coating through the Letomec sensor Helios 2, and we were able to characterize the different traps that were present in the material as dislocations. So thank you very much for your attention.
The next speaker is Aouafi. He's a senior research in ArcelorMittal. He's a project manager, and also he works in automotive products properties department since 2010, in charge of projects dealing with the hydrogen embrittlement topics. So Anis, the floor is yours.
Yeah, thank you, Linda. Thank you, Sílvia, for this introduction. Hello, everybody. So today I'm in charge to present you the results that have been obtained when dealing for mechanical characterization of the hydrogen embrittlement during this project. Let me just first have a brief summary of all the tests that have been tested. I think Sílvia have mentioned them in the introduction. Two first tests that they have bending solicitation, the famous or well-known 4-point bending test. I will go in detail for this test later. The U-bend test, which is used to simulate forming process. And as you can see here, I take my pointer. As you can see here, we simulate the bend, and then we use the screw in order to keep the sample under deformation. The other tests that have been used are the constant load test, and the principle of this test is to impose a constant displacement using this kind of device, which is called the proof ring device, and which acts as a spring and to maintain the sample under constant displacement. The two other tests are slow strain rate test or the least linearly increased stress test, and this use a tensile machine in order to apply a constant increase of loading at various strain rate at various strain rates. The other test that have been used is the incremental step load test, and this one we also use the tensile machine in order to apply an incremental step loading during the test. The last test that have been used is well introduced this morning in the toughness project is the crack resistant test, the essential bulk of fracture that, and we will show you some results using this test in the hydrogen embrittlement field. So what is important to highlight that some tests have been used for both internal and external hydrogen. What is meant by internal hydrogen is to test the internal hydrogen which comes from processing of the material, or to simulate it by, as mentioned by Mélodie before in the presentation before, we electrochemically charge the sample and to put the zinc coating in order to avoid degassing. Or for press hardening steel, we use a different condition in order to outgas charging the materials. So some tests are used for internal and external hydrogen. One test is used only for external hydrogen, and the last test is only used for internal hydrogen. For external hydrogen, we have made the choice to use two different medium. The first one is immersion in salt water with the pH 4, and the other one is a cyclic corrosion test which simulates salt spray chamber. So for the external test, it's worth to mention that all the tests undersea baking heat treatment before test in order to be representative of what the real part on the vehicle foresee during the cycle life of the material. For the edge quality for cold rolled steel, as mentioned by Sílvia in the introduction, sheared edge or punched edge are used for cold rolled steel for all specimen, and for press hardening steel, all the specimens have been laser cut. So here is just a brief introduction of all the tests that have been performed. Today, I will not show all the results. I will just highlight some results. Let me begin, first of all, when we characterize the internal hydrogen using the 4-point bending test. So the principle of this test is to impose a constant displacement using a screw here, and we measure the displacement using this comparator. This displacement is correlated using a formula in the let me say, in the elastic domain, is correlated to the applied stress using the setup geometrical parameter, but also the material property like the thickness. So this test have been applied during 4 days on the press hardening steel and controlled steel with different internal hydrogen content. And the results are summed up in this slide. For press hardening steel, where the specimen are leather cat, we could obtain for all material such delayed fracture map with the applied stress versus diffusible hydrogen, and when the crack occurs, it's highlighted by a red point. And with this graph, we highlight the delayed fracture map that we could obtain using this test in this condition. On the left, it's highlighted the obtained delayed fracture map for MS 1500, and in this case, the edge was sheared. So we could not compare the behavior of MS 1500 regarding PS 1500 because the different type of cutting have been used for both material. Another remark, and as mentioned by Mélodie before, we were not able to have enough tie zinc coat on the CP1200. We are still working on it. We are surprised of that, and we were not able to have equivalent delayed fracture map compared to the other materials. The second result that I want to show you, and we have chosen to show you today, we make the bridge with what we have been presented this morning, and to apply the essential work of fracture methodology for hydrogen embrittlement topic. So the principle of the test, I think the detail have been mentioned this morning. What it is, so the specimen is a double notch specimen, and they have been used on specimen that have been electrochemically charging for controlled steel or hot charging for press hardened steel, and different strain rate or velocity have been used for this test. So the results that have been obtained, and here I will focus only in the case of CP1200. So the principle of the test have been detailed this morning. So what is shown here on the left, on the top, the total work of fracture that have been obtained with different hydrogen content. And as you can see here, for different ligament, we can highlight that using this kind of test, essential work of fracture, we can discriminate the effect of hydrogen and the effect of different content of hydrogen using for this parameter the total work of fracture. The same conclusion could be also we have the same conclusion regarding the essential work of fracture, and as you can see, the essential work of fracture drop when the hydrogen content increase in the specimen. So here I show you the results, the good results that have been obtained using this kind of methodology for CP1200. Unfortunately, for MS 1500 and usable 2000 was not really easy to obtain, and this is the limitation of this kind of methodology, because for a higher grade like martensitic and usable or press hardening steel, we are not able to differentiate the different hydrogen content. So further work need to be done in order to adapt this kind of methodology for higher higher grades, and maybe some alternative parameter could be used in order to discriminate the effect of different hydrogen content on the response of this test. The third and the last result that I want to share you is the result obtained when characterizing the external hydrogen effect. So the hydrogen comes from corrosion during the cycle life of the vehicle, and we use the same test that has been shared before for point bending test in two different medium, as I've said before in the introduction: immersion in the salt water with pH 4, or application of cyclic corrosion test, or salt spray, the well-known salt spray test. Here are some photos in order to illustrate how the fault bending tests have been immersed water or put in the cyclic corrosion chamber in order to foresee the desired cycle. So for press-hardening steel, laser cat have been used, and cold draw steel, the shearing cutting have been used. So the first result I want to share you, and the results have been obtained by voestalpine concerning the press-hardening steel heat-treated. I need to mention that all the tests when we are dealing with external hydrogen foresee paint baking in order to be representative of the real case on the cycle life of the part on the vehicle. So as mentioned by Sílvia in the introduction, different heat treatment have been used for these two grades, PS 1500 GA and the usable 2000 ice coating. And as you can see here, the result obtained in immersion in salt water or SST for different applied loads. So we vary the load from 1% of yield strength to down to 40% of yield strength. And both materials don't foresee any crack. No failure have been observed using this test in this condition, independently of the heat treatment. The other results concerning cold-rolled steel, and here the table sum up as before all results that have been obtained. So first line concerning the CP1200 electrogalvanized, the condition here are the targeted internal hydrogen that have been targeted for the reference 0.6 ppm and 0.8 ppm before paint baking and before immersion. So that's why I highlight that this content concern the hydrogen content before paint baking. So the CP1200, we will not see any crack for the SST, the salt spray test, or the immersion test up to 100% of yield strength. For MS1500, on the reference material, so the material at the delivered state, the material is safe. There is no crack have been observed. And while we combine the internal hydrogen to exposition or to the environment, or medium hydrogen coming from the medium, some crack have been observed at 1% of yield strength and 80% of yield strength. Just I want to highlight that some measurement of the hydrogen for both material. Let me take the example of 0.8 ppm for CP1200 before testing in the medium or in the corrosion. Just after paint baking, only 0.1 ppm left in the material. For the case of MS1500, and we obtain a different result, and so 0.8 ppm before paint baking remains 0.6 ppm after immersion. So this highlight that the crack that have been observed here is probably induced by the initial hydrogen charging from 0.4 to 0.8 ppm, which is not representative of the material, of the reference material. So it's a highlight that the impact of internal hydrogen is not highlight the impact of the external hydrogen in this case. So another work that has been performed in this working group, and we want to share you this work So we have tried to classify the mechanical tests that have been used. The objective of this work is to give you an overview of a classification according to different criteria. These criteria have been grouped into families. The first one concerns the complexity of the sample preparation. I think it's important to keep this on mind. The second one, or the second family, concerns the suitability of this kind of mechanical testing for hydrogen embrittlement risk. And this graph highlights, or this table highlights different criteria that have been taken into account in order to classify the complexity of the sample preparation. So here, for all the tests that have been performed in this project, we have classified from simple to complex, like the sample geometry here, the required specific tool, if it is a conventional specific tool or a specific one. So the sample preparation cost, I think it's important to keep this in mind, which is low or high, and we have tried to classify this kind of test. And for example, for this graph, the 4-point bending test, which is the largest square obtained, could be the best one concerning the complexity of the sample preparation. It's the easiest sample could be prepared. The second classification concerning the suitability of the mechanical test for hydrogen embrittlement, and here we have tried to classify among different criteria. The first one is the test duration, the cost of one trial, the machine availability and relative costs. If we need a lot or a small amount of specimen, I think it's important for each lab to know that and to take into account while choosing one test versus another. And here, the sum up and the comparison of the different used tests during this project. The second chart concerning the suitability, also, we have tried to classify this mechanical testing if there is a necessary test reference in order to be comparable. At the air, for example, the test is standardized. I think it's important. It's a major point if it is standardized in the field of hydrogen embrittlement. And here we mentioned the ISO standard, the STM, the VDA, the work in the VDA groups, guidelines from a certain OEM. Ability to define standard deviation is important, and is there a lot of parameter or a small amount of parameter comes from the output of such kind of test. But also we need to take into account the complexity of data processing. I think here we have tried to classify all the tests based on what we learned during this project, but also based on the know-how of each partner. Here, I don't want to highlight a test compared to other. The idea is to give you an objective classification. We do not recommend or promote a test at the moment, at least. But each person or interested person could choose according to his technical and budgetary constraint the appropriate test. So part of the conclusion of this work, we have characterized 4 different grades with the different tests, large amount of tests. We have tried to characterize the hydrogen, which comes with the internal hydrogen, which found in the material, but also the external hydrogen, which come during the corrosion of the material during the cycle life. But also we have tried to highlight if there any combination of both phenomena. I need to highlight that for all these tests, different mechanical loading have been chosen: tensile, bending, incremental or constant, different specimen geometry, rectangular, but also we use the SAP, the famous SAP 1970 specimen, different initial hydrogen content, even electrochemical electrochemically charging for cold steel or hot gas charging, and different mediums. So for each test, we obtain a certain SEC threshold. So the remaining work, and we hope we are still working on it, is how to make the correlation between these various tests. And during this work, also we have tried to give you an objective classification of these tests based on the knowledge learned during this project, but also the know-how of each partner. So here I finish my presentation. Thank you all.
Thank you, Anis, for your presentation. Now it's time for the last presentation. She's Linda Bacchi from Letomec. Now she's working in Letomec, a spin-off company of University of Pisa, dealing with hydrogen embrittlement phenomena in various materials for several industrial sectors, from automotive to home appliance, energy and steel making. She also contributes to the research activities by performing laboratory tests and collaborates to the development of a patented line of instrument, fully dedicated to the investigation of hydrogen-metal interaction. So, hello, Linda.
Hello.
The floor is yours. Hello.
Good afternoon to everybody, and thank you, Sílvia, for the introduction. Now we are going to focus on a series of diffusible hydrogen measurements that were performed online at industrial level with innovative technology. First, we have a brief introduction of what is the hydrogen embrittlement in automotive industry. Then we are going to focus on the HALIOS technology and the description of the methodology that we have adopted for the testing. Then we are going to move to the results of the Crystal project, and finally some conclusions. All of you already know that the environmental norms push for the reduction of emissions. So for sure, automotive industry has to reduce, among other things, the vehicle weight. And one way to do this is to use materials with improved performance. In this case, advanced high-strength steel could be one of the nice choice to do this. The only thing that we should also consider to take into account during the design of the vehicle is the hydrogen embrittlement, because higher material performance involve also the risk of hydrogen embrittlement. As already said by Sílvia before, the hydrogen can be absorbed in different steps of the part production, from the steel making to the vehicle manufacturing, the part manufacturing, up to the operative life of the vehicle, for example, due to corrosive phenomena. And what is important in this case is to understand which is the absorption of hydrogen inside the metal. For the moment, there are several technologies that allow to perform the hydrogen measurement, and some of them are the oedometers, the mass spectrometer, also the thermal desorption analyzer. All of them are very good technologies, but they present some limitations for the application at industrial level, for example, for the quality control of the processes. These limitations and these gaps gave us the chance to design a new device which could be used at industrial level and which is based on the same methodology, which is the hot extraction, but is very easy to use for the quality control. This device is the HALIOS 4 hot probe, and how we think that it should be used. It should be used for the quality control, picking the device in the plant. The device is a portable equipment and can be easily applied to the part or the coil directly to the finished part. There is no need to cut the sample. There is no need to remove the coating. You have a very easy instrument to perform the diffusible hydrogen measurement on bare and also coated components. The important thing to understand is that, of course, you have to use it as sort of a traffic light, let's say, because you will not have the same precision of a laboratory device, but you can understand if your process is going out of control. So every measurement can be compared, for example, to the behavior of the material for different diffusible hydrogen content and understand if you are going toward the critical value. Another important thing that also for this instrument in the past, in the recent project Horizon 2020 Form Planet, we have been also able to realize and publish a CWA dedicated to this instrument, and in particular to the methodology that should be used to apply this device. You can read this CWA online, you can find it, and we realized this CWA together with the collaboration of the other partners of the other project, and in particular with the Spanish Association for Standardization. But now we can move to the core of the presentation, and in particular to the results of the project. One of the objectives of the project was to understand which is the effect and which is the absorption, the hydrogen absorption in the material during the manufacturing process. We realized a couple of industrial case studies. The first one was on usable 2000 with the typical coating, which is aluminum silicon. We realized a series of components. In particular, we defined the A-pillar reinforcement in this case, and we stamped these parts by making some variation in the stamping process. At Cassino plant, we were able to modify both the dew point control, so we made different, we changed the dew point control by switching off the dew point control, and so also increasing the temperature inside the furnace, the dew point inside the furnace, and also we varied the dwell time of the process. After this hot stamping, we realized a series of diffusible hydrogen measurement by means of the Helios 4 hot probe. And in this case, we found a couple of areas that were identified as A and B on the component. Here you found the statistical evaluation of what we have found on this experimental campaign. We found very low hydrogen content almost in all the components and in both the areas that were analyzed. The maximum value that we found was 0.2, and the average value was 0.1. However, if we compare to the literature value, the critical threshold value for hydrogen embrittlement of this specific material that we found online and is represented by the red line, all of the measurements that were performed were very lower. The second case study was realized on the PHS 1500. In this case, this material was galvanized, and we defined a different component, which was the B-pillar. Here it's represented a part of the B-pillar because we need to ship these parts from the Voestalpine plant to our lab because due to the COVID situation, there was no way to reach the Voestalpine plant. So we received the component very fast, and we performed the measurement of diffusible hydrogen in the 4 areas that you see here highlighted in red squares. In this case, at Voestalpine plant, there was some difficulties in changing the parameters of the process, so we had the possibility to change only austenitizing temperature and dwell time. Also in this case, we have reported here the statistical analysis of the measurement. We made a lot of measurement on several pieces, and the maximum value that we found was 0.1, but however, the average value of all the measurements that we have performed was 0.0. So I think that we can say there was negligible diffusible hydrogen content almost in all the pieces that we received from voestalpine. And this is the conclusion related to the industrial measurement on components. Then, still within the frame of Crystal project, we performed additional measurement. In this case, the measurements were performed after cyclic corrosion test. As already mentioned by Sílvia, we planned to perform measurement during 4 live tests. This was not possible due to several reasons, but we substituted this testing with the cyclic corrosion test, which is a laboratory test, but can represent, however, in 6 months, the same of 15 years of operation. So we realized some coupons that were small sheets, maybe 100 by 200 millimeters, and we put them in the cyclic corrosion test according to the standard. On this sample that we cut, we realized for the 4 materials under investigation, we decided to test 3 different conditions. The first one was without the cataphoretic coating. The second one was with the cataphoretic coating. And then we decided to add one more condition, which was the application of the coating and then simulation by stone chipping of a sort of damage on the surface. Here, just as an example, because samples were very, very numerous, we reported here for the PHS steel only some images from the testing. In particular, we have selected the samples after e-coating and stone chipping. And as you can see here, over the time is very clear how we can appreciate the increasing of the red rust. And also, I can tell you that we appreciated also the metal dissolution of the material. But however, in all the cases, the diffusible hydrogen content inside the sheets was very low. We performed the same evaluation also for the cold rolled steels. And here there are some images of the samples, still considering the sheets with the e-coating and stone chipping. And unfortunately, we performed a lot of measurements, but not only with the Helios 4 hot probe, but we decided to repeat some measurement also with the typical TDA analyzer. And we were not able to appreciate any trend in the hydrogen absorption. What we discussed together with other partners of the project was that maybe we can have some very local hydrogen accumulation, and so all of the testing methodology that we can apply are considering an average measurement of a certain area or of a certain part of the sample, and so we were not able to assess the hydrogen embrittlement risk during this corrosion testing. I think that we are to the conclusion. So we were able to perform some diffusible hydrogen measurement by means of Helios 4 hot probe. We were able to do this maybe also online, directly on components, and there was no need to remove the coating on the samples. During the industrial case studies, we observed negligible hydrogen absorption in both case studies on pre-hardening steel, while for concerning the cyclic corrosion test, it was difficult to identify significant or appreciable hydrogen absorption during this accelerated corrosion test, maybe due to very, very local hydrogen accumulation. So that's all from my side. Thank you very much for attention.
Thank you, Linda. So now we have concluded the presentations of session 2, and it's time to questions and answers. If you have some questions, please write it down on the chat, and if it's on site, please. Jaume?
Hi. Thanks for a nice session and very interesting presentations overall. I have one question if no one else has any other right now, so I will be the first. And I'm going to be a little bit polemic, but this is for Mélodie and for Anis, actually, but for all of you. Mélodie has shown us that the most relevant parameter in charging hydrogen basically was the presence of nitrogen in the atmosphere. But for the other parameters, including the dew points, the maximum that you ended up having was something like 0.12 ppm or something like that. It was for press hardening still, sorry. But from the results from Anis, we have seen that the problems started to appear when we had more than some 0.25 ppm or something like that. Does this mean that hydrogen embrittlement is actually not a thing? Because if in normal conditions in press hardening we don't charge more than 0.15 and more than 0.25 is not a problem in mechanical properties, then?
Maybe you can simplify the question.
Yeah, the thing is that the amount of hydrogen that gets in normal conditions in 15 degrees Celsius dew point in press hardening apparently is not enough to cause hydrogen embrittlement problems.
Yeah, it's the case, and that's why we try to perform exotic charging in order to increase the amount, in order to have access to the delayed fracture map. Unfortunately, for press hardening steel, the case of press hardening steel, there is a shift between 0.2 to 0.5 or 6. We are not able to have between
values in the middle of this range.
In the middle, yeah, it's really technical point of view, and even for electrochemical charging, we were not able to have a small amount of hydrogen content in the material. It's really a technical point of view problem during charging hot gases or electrochemical charging.
Okay, thank you. There's just another small thing. You said that in nitrogen atmosphere, the uptake of hydrogen was completely out the charts, so it was one order of magnitude more than any of the other cases. Okay, this is not an issue for press hardening or hot stamping of coated boron steel, but for uncoated boron steel, which kind of atmosphere is used in the furnaces? Maybe there is someone from a stamping company here, because I thought that it was nitrogen atmosphere, but maybe it isn't. Because if this were the case, it is super concerning.
I don't know if Anis or Linda can answer this question.
If we well understood, we applied nitrogen atmosphere in the furnace also for the bare steel AHSS after removing the coating, if this is the question.
Mm-hmm.
Yes,
So,
but for the results that we obtained for the PHS 1500, they were performed on the bare steel. And they were performed with nitrogen and air in order to compare both of them. But we are not at an order of magnitude of difference for that steel. The results were quite more impressive, I would say, for the LEC coated UZ-Bar 2000 than for the PHS 1500. The difference was less significant for the bare steel, actually.
Okay. Okay, thank you.
Okay. We have some questions from the online attendants. One for Linda.
yeah.
What temperature is the material heated in order to extract the hydrogen? Is it possible that this heat treatment changes the microstructure?
No, because we are going to reach very low, let's say, temperature. In particular, in the case study that we have done within the frame of Crystal project, we reached not more than 200 degrees. So in order to enhance the hydrogen diffusion, but not to damage the coating or the material, or make some changes to the material.
Okay, thank you, Linda. Another question for you. How Letomec proof is different from the hydrogen permeation test using the Davanatan cell? Letomec proof is more accurate than the DS cell? Thank you.
We cannot say that is more accurate, but it's a very simple methodology with our device. We made some comparison with a traditional device, and we get very good correlation. We were not able to present them here because it was not the focus of the Crystal project, but on some publication maybe, and also if you contact us directly, we can present you some details about this correlation. Thank you.
Thank you, Linda. I think that it's one comment about your question, Jaume, about the... Okay. The content of hydrogen in ppm is dependent on the thickness. The lower the thickness, the higher the ppm. Nitrogen is important in case of aluminium silicon coating, as it prevents the oxidation of the coating. Aluminium oxide is barrier. With nitrogen, the formation of aluminium oxide is reduced.
Okay, great, thanks.
Okay. So, Wolfgang, thank you.
Thank you.
Okay. Another questions?
Yes, I guess this question is for Anis. I have seen in the test the austenitizing temperature in different values. The maximum temperature is 920. My question is if it really is, it is really a red line to increase and to do tryouts with more temperature than 920.
Yeah, the chosen parameter or heat parameter for usable 2000 is within the process window that we recommend in order to have a lower hydrogen content during processing.
Okay. And I have one question for Mélodie. Can you explain in more detail why is deuterium used for the trapping characterization?
Yes. So for the trapping characterization, we choose to work with deuterium. Actually, deuterium is very interesting because we can, it's far more scarce than hydrogen, actually. So we are sure about the step at which we introduced it in the material. So what is interesting is that for electrochemical charging at ArcelorMittal, they were able to replace water, so actually the H atoms in the water by deuterium atoms, so by deuterated water vapor, and we are also able to do it at using in the controlled atmosphere furnace, so for the gaseous charging, by replacing the ordinary by deuterated water vapor for the humidification of the gas, actually.
Okay, thank you, Mélodie. Any more questions? No? So thank you very much, the speakers and the attendants, and I think that we have now a short coffee break, and we'll meet here at 14, sorry, at 14. Okay, thank you very much.
Thank you.
Thank you. Bye.